Hello. Now we're going to go back to chapter 3 and discuss the famous Jordan-Hildur theorem. And this is one of the major results in group theory. And so in undergraduate courses or Algebra 1, they often talk about the isomorphism theorems, and sometimes they'll talk about this theorem without giving the proof, but we're going to give the proof. And so one of the things you study in a normal undergraduate course is this notion of normal subgroup and this notion of quotient group. And so the isomorphism theorems tell you a lot of facts about isomorphisms between subgroups of this quotient group and subgroups that sit between N and G. And we've already been using some of those facts with the CELO theorem videos already, as I'm sure you have noticed. But one of the things you could talk about is trying to expand this notion of normality. And so I'll discuss this by example. We've already seen that S4 has a normal subgroup called A4. But A4 also has a normal subgroup called V4, the Klein 4 group. And then that group has no normal subgroups. And so we have this chain of groups inside of S4. Well, let's be careful there. V4 is an abelian group of order 4. It contains a subgroup of order 2. And all subgroups are normal, and so you've got this maximum chain. And so the question is, well, can you decompose a group into a sequence of chains of subgroups such that each group is normal in the next one? And so this is the notion of a subnormal series. Where you require it's a sequence of groups where each group is normal in the next group. Notice, of course, we are not saying anything about whether or not they are normal in G. They might be, they might not be. That is not a requirement. So, of course, one can always ask, given one of these sequences, can you make it longer? Which ultimately comes down to, if I have HI is normal and HI plus 1, can I insert another group in between them? Namely, can I find an H prime that is normal in HI plus 1, but contains HI? Does such an H prime exist? Why do I have only containment here? Well, because it's a known fact that you can check that since HI is already normal in HI plus 1, it's closed by conjugation by HI plus 1. Since H prime is assumed to be a subgroup, when you're conjugating by elements of H prime, each of those elements is in H. Yeah, I guess we can just do the proof. If X is in H prime, then it's in HI plus 1. And so X, HI, X inverse is already equal to HI because you're assuming HI is normal in HI plus 1. And so the point is, in one of these sequences, if you could find a normal subgroup lying between them, then you can make the sequence one step longer. And so let's assume for the moment that we're talking about finite groups. Well, how far can you take this process out? Well, obviously the longest you can get is when you can no longer do this. When for any pair of groups you can't find a normal subgroup sitting between them. However, by one of the isomorphism theorems, such a group would correspond to finding a normal subgroup inside this quotient that's non-trivial. And not the whole group. So then the question becomes, whenever you have one of these pairs, look at this quotient. Does this quotient have any non-trivial normal subgroups? If it does, applying the isomorphism theorems, you can extend this subnormal series and make it longer. So the longest subnormal series you can get is one where you can't do this. And that's the definition of simple, as we've seen already. If whenever you have a normal subgroup, it's either the trivial group or the whole group. And this Jordan-Hildur program theorem is where this notion of simple, at least one of the places where it arises. The point is that once you get to this point where each of these factors has a simple quotient, then you can't make the series any longer. In other words, suppose you've got a subnormal series. And gi plus 1 mod gi is simple for all I. Then you can't make the series longer. I would say maximal, and so students who've had me in discrete math courses will know when I say maximal instead of maximum, that means that you can't make anything longer that involves these k terms. You might need to use something else, and it's possible that you might get something longer. But at the very least, this is as big as it gets with these k subgroups. There's no way to insert another subgroup somewhere in the middle. In this case, this is called a composition series. And the GI are called factors. And so the example I had previously is actually a composition series. You can check that my example with C2 sitting inside V, sitting inside A4, sitting inside S4 is in fact a composition series because Z2, V mod Z2 is isomorphic to Z2. A4 mod Z, V is isomorphic to Z3. S4 mod A4 is isomorphic to Z2. Each of these is a prime cyclic group, and prime cyclic groups have no non-trivial subgroups. Therefore, they must be simple. And we already proved in the previous video that alternating groups for n bigger than 5 are also simple. And so this is a composition series. This example is slightly bad because you can check and discover that there are no other composition series for S4. Mainly because there are no other normal subgroups of S4, which takes a little bit of effort to prove. If you go through the CELO theory, the CELO 2 subgroups of S4, there's exactly 3 of them. They're all conjugate. They're all isomorphic to the dihedral group D8. And the fact that there are 3 of them means that they are not normal subgroups. Ergo, there's no normal subgroup of order 8, so there's no subgroup of index 3. That is normal. And just think logically, what else can you get? Well, whatever the index is, when you quotient by it, you're going to get a group of that order. So it's got to be order 2 or 3, or 6 or 12. And, well, as we already discussed, for simple groups, for small simple groups, you're going to have z mod pz, so 6 and 12 are right out. It is true that V is normal in S4, but as we saw, it's not the largest normal subgroup you can get, because that subnormal series can be refined by inserting this A4 in here, as can be seen, but because the quotient of S4 mod V is not a prime cyclic group. So let's look at another example. This one is from the book. Let's look at D8, the dihedral group on 8 vertices. Let's take the trivial subgroup, which I'll just denote by 1 for simplicity. And let's take the subgroup generated by a reflection. Oh, wait, not that one yet, because that one's not obvious. Let's see, we're talking about the dihedral group of the square. Let's take a normal subgroup. Well, there is a natural normal subgroup consisting of S and R squared. That is isomorphic to the Klein-Fork group. That's also the symmetry group of a rectangle instead of a square, because you can do the 180-degree rotation in one of the reflections. And you can check that it is normal. And then inside that group, you end up getting S as a normal subgroup. But that's not the only composition series for the dihedral group. The other composition series is that we all know that the rotation group is a normal subgroup of any dihedral group. And the square of the rotation is a subgroup of R in this case. And so composition series are not unique. However, in this example, you can actually check that each of the quotients is isomorphic to Z2. So you get Z2 no matter what. So here comes the theorem. That's due to Jordan and Hildur. You let G be a finite group. The first part, composition series exists. That one is not that hard to prove. And the second part is, suppose you have two composition series for G. So there's one composition series and another composition series. Let's say that you're going all the way to 1, of course. HR is equal to G. Then it turns out that K is equal to R. So while there might be more than one composition series, they all have the same length. Moreover, you can write down a bijection between the integers 1 through K to the integers 1 through R, such that Gi plus 1 mod Gi is isomorphic to H sigma of I plus 1 mod H sigma of I. Oh, let me get that parentheses correct. Hey, look, the textbook actually got the statement right. So sometimes they say things are correct up to permutation, which is always kind of a weird statement, but this textbook actually makes that precise. The point is that you're guaranteed to have the same length, but more importantly, all the quotients are actually isomorphic, that appear in both sequences are isomorphic up to some ordering. So in other words, if you write down the multiset of quotients, you're going to get the same multisets up to isomorphism. The book says the proof is fairly straightforward. It actually takes some effort. We will actually give the proof because it is worth knowing. but not in this video. Right now it's just enough to know this theorem because it's a pretty important theorem in the history of group theory. And so the main punchline is that you can decompose groups into simple groups. And so sometimes they say simple groups are the building blocks of group theory. And so this is important because, well, you can see it as a generalization of the following theorem that some students know from finite group theory. From other classes possibly. This one I won't prove in this course because it's kind of tangential. Suppose you have a finite abelian group, then it decomposes. According to this theorem, it decomposes into quotients that are into these quotients, but you can actually prove that these quotients in that case, well, they have to be simple groups that are abelian, and you can prove that well, just think about it. A simple group that's abelian, every subgroup is normal, so you have to have, because you're abelian, and the only normal subgroups are the trivial group and the whole group. So in other words, the only subgroups are the trivial group and the whole group. The only quotients are the prime cyclic groups. So we already know exactly what the building blocks are. The building blocks are the prime cyclic groups. But of course, some of you probably already know this theorem. The theorem is that you can decompose your group as a product of power cyclic groups. And so this is an analogous theorem. The only difference here is that the construction is a bit weirder. Namely, the main difference between these two theorems is that given an abelian group, if I know its prime power cyclic factors, I know the whole group. Given an arbitrary finite group, if I know its simple group quotients, I do not necessarily know the whole group. That doesn't tell me how to actually construct the composition series. It doesn't tell me how to construct G. The reliance here is that for abelian groups, G is always isomorphic to the direct product of its normal subgroup and its quotient group. That's not true for groups in general. So here was the Jordan-Hildur program, which essentially ended in miserable failure. It was to study the following two problems. The first problem was classify all simple groups. That problem was finished, although it is non-trivial, which is a very gross understatement. I'll talk about it in another video, or in the next video in this series, because it's actually an interesting problem with a unique history. But the other one is to find all ways of putting groups together. In other words, given two groups, let's call it N and Q, find some sort of construction to get all groups G with the property that N is normal in G, and G mod N is isomorphic to Q. We have no idea how to do that step. And why is this one relevant? Because the whole point of the theorem was that every group has this composition series that breaks it into pieces. This is classify all the pieces. This is classify all the ways you can put the pieces together to form your groups. If you could solve these two problems, then you will have created a procedure to create all groups constructively. We have no idea how to do that. The only progress we have towards 2 is that we have this notion of semi-direct product that we'll mention later. That describes all cases where you have a normal subgroup G. G mod n is isomorphic to Q, and somehow Q is still a subgroup of G. And under this embedding, Q and N intersect in the identity. If you have that set up, then we know how to build your group. But if you don't have that set up, we have no idea. The only other construction we understand is if N is abelian, and you want to insist that N is a subgroup of the center of G. They call this a central extension. So you're adding two extra requirements, starting with an abelian group and another group Q. Find all G such that N is a subgroup of the center of G, and G mod N is Q, isomorphic to Q. And that construction involves a chapter we're skipping. That involves something called group cohomology. Namely, the set of such G, such that N is contained in the center of G, and G mod N is isomorphic to Q, is an abelian group in some sense. There's some sort of equivalence relation you have to work out. And it's actually very, very complicated. But up to that structure, you get an abelian group, and so a finite abelian group, and so you can use the fundamental theorem of finitely generated abelian groups to classify all these elements. You can use that to classify all such groups G. If you're not in these two cases, we have no idea how to construct all possible groups G with these two criterion. All right, what about step 1? Classifying all finite simple groups. Well, there exist 18 infinite families. Of simple groups. That, of course, is a strange phrasing. So what they mean is that we know how to classify them. The first family is indexed by primes. It's just the prime cyclic groups. The second family is the alternating groups, where n is at least 5. The third family consists of taking the special linear group, so n by n matrices of determinant 1, quotienting out by the center, and the entries must come from a finite field. And it's a theorem that you prove later in an algebra course, that every finite field must have prime power order. So they point out that these things are indexed, but I mean, this infinite family here has 3 different parameters. So there isn't just one group here, or one sequence of groups, or one infinite table of groups. It's one 3-dimensional array of groups. One index for every odd prime, one index for every power, one index for the sizes of the matrices. And I can tell you now, the other 15 group infinite families are more like this one. They're things that look like matrix groups, but they eventually get really, really complicated to describe because they get involved with something called Lie groups, and yeah, I don't even understand it all myself, but the point is there's a lot of these. And then there's 26 other special cases that are called sporadic. So these are 26 groups that defy classification. They don't belong in any of these 18 sequences. And one of them is called the monster group. I might talk about it at some point. It is really, really big, although I've seen mathematicians point out before that there are plenty of groups in this infinite family that are actually significantly bigger. But this group was found when they were trying to prove this classification. So it was found by accident. They didn't know it even existed. And they discovered it existed, and it's really, really big. And it's actually generated by two elements. And yes, we might do the proof that this group is simple, but we're not going to go through the whole classification because the classification theorem takes 10,000 pages or something. Wait, let's see, what do they claim? Yeah, 10,000 journal pages. In fact, it's not even clear that the proof is complete. As I remember, sometime in the 2000s, they found another gap that they had to fix. And so it's possible that it's not entirely true. In fact, one of the theorems in the area is the celebrated Feit-Thompson theorem, which just says that if G is simple of odd order, then G is isomorphic to Z mod P. That's not actually what they originally said. If I remember correctly, it says if G is a group of odd order, then it is solvable. And so then, but that requires the notion of solvability, which we'll get to in a later lecture, but I'll at least point out the actual theorem. Wait, hold on, let me say. If G is odd, then G is solvable. And you'll see how that implies this. That proof alone takes up 255 pages. So this stuff is very, very difficult. I should point out you could call this a two-parameter family if you just say that this is Q and Q is a prime power. So I will state most of these infinite families are two parameters. A few of them have only one parameter, like these two. And there's nothing worse than that, at least. But you can clearly see how this is significantly harder than the corresponding theorem of finitely generated abelian groups, which only has this first row as its basic building blocks. Or the corresponding theorem for finite fields, which basically says that the only finite fields are these ones. Now, there's also a notion of simple ring. The classification theory for finite simple rings is actually completely trivial. They end up being n by n matrices whose entries are in a finite field. And so again, there the classification is simple, but here it is ridiculously horrible.